Henrik and I think your colleague Eric, right?
Eric is the main contributor of the coding.
Correct.
Yeah.
So they have actually written the AODV UU routing protocol, which some of us are using here. So that's just a brief background. So without further delay, I'd like to welcome Henrik and Theodoros and hand it over to you.
Thank you.
Sure.
Thanks for the introduction. We are very pleased to be here. We're going to give a talk today about our mesh networking project at Thomson, and we titled it Multi-Layer Architecture and Max-throughput Routing. So it's me and Theodoros. We have an intern called Mariana Carrera. We have a past intern called Ming Li, who has done something I will present, and Christophe Dior, which is the head of the lab. So just showing what the Thomson Paris Research Lab is about. So it started in the fall 2005. The official inauguration was in June 2006. So we have currently now we have 2 admin people. We have 4 permanent researchers. We have 3 postdocs, roughly about 10 interns and 5 visiting faculties each year. Mostly during the summer, I would say, but we also hire interns throughout the year. The lab has domains of research. So we're doing peer-to-peer, and in this product we're mainly doing algorithms for content distribution. We have a network analysis project where we are looking at anomalies in the data collected by the main routers on the internet. We have a pocket switched network, which is more disruptive, delay-tolerant network, where we look at the end-user mobility, we look at the forwarding algorithms, etc. And then we have the wireless mesh project, which is what we're going to talk about today, or the WIP project. So we are funded by the European Commission for 3 years, and we're working together with 7 other partners, some industrial and some academic in Europe on this project. I don't know how necessary this slide is. Speaking at the Orbit Lab, I assume that everyone knows what a wireless mesh network is. I tried to come up with some definition. A peer-to-peer multi-wireless network where the mesh routers have redundant links and forming a backbone trying to cooperate to route packets to destination. But for the end-user client, this is just a normal Wi-Fi connection, and you don't really care what's behind your access point, if it's multiple links, 10 hops, 1 hop, or it's a wire. So, of course, you also notice that the mesh is already happening. You have a lot of grassroots deployments. You have community networks. So I found a number of 248 mesh networks being deployed worldwide. You have in Houston, San Francisco, Mumbai, Kingsbridge, and whatever. You have academic networks, like RoofNet was one of the first ones. You have the RISE TAP project, which Theodoros worked on. You have the UCSB mesh network, which I worked on. And you have a number of other academic projects. These are mostly targeted to perform real research compared to others which are more with users. There's also a lot of industry, riding on this wave and developing hardware and software for these solutions, like Tropos and FireTide, Strict System, Packet Hop, etc. And you have a typical number of scenarios that you are targeting, such as community networking, disaster area, public safety, etc. So this is just to establish some ground, and you have a number of research challenges. This is, of course, everyone thinks that these are different. So here are some of the things that we have been thinking of. So it's to make your protocol interfere and high density aware. So if you think that you have a community of access points, let's say everyone at home has its access point, a regular Wi-Fi, and you imagine that you want to put some mesh networking software on that and make these guys collaborate and form a number of community networks, you will have to care about this. For example, in my apartment in Paris, I turn on my wireless and I check how many wireless access points can I see. So I see about 50 access points for my apartment. And so one other thing is that out of these 50, about 30 operates on the same channel, which seems that most people just plug it in and run, and it's the default setting. So you have the same channel, you have maximum throughput and everything. So this is something, if you would have some mesh there, you would really want to take care about this. Other problems are more how you construct your topology in the mesh networks and how you can utilize cross-layer information in this and how you select your gateways, etc. Also, from algorithmic perspective, you want to understand, can we model this to come up with distributed self-organizing algorithms, and do they lead to a global optimum giving your objective function that you have defined? There are also some other ones, maybe less research, but still you have an operational perspective if you think that these would really happen in reality, where you have this network. If there would be real users at the end, it has to be available almost all the time. So that's a big issue. And I think also the management, what do you do if your neighbor turns off his access point or not behaving correctly? How do you do that? How do you not end up being like the guy in the corner, just being very frustrated that, oh, this is the mesh network? Ideally, it should be completely transparent for the user. So here's the outline of the talk. So we'll talk about an overview of the testbed that we have at Thomson and some hardware that we have. I will also talk about one model that extends the current routing metrics. After that, I will hand over to Theodoros, who will give a talk on max-throughput routing, and who will also conclude with some research directions that we have. So we have a deployment at the Thomson Paris lab. Right now, it's 12 nodes. It's multi-radio nodes. They are located mainly inside our lab at this point, but we also have a few nodes being outside on the parking lot under roof, and we also have the headquarters building next to us, which is a huge building where we are currently deploying nodes. So hopefully we can deploy a slightly larger testbed in the future. And all these nodes are being deployed with a wired backhaul, so you can perform management and all that kind of control. So what's the device that we're using? It's a mini ITX motherboard, which I think seems to be the same size that you are using here. But this is not a VIA, but it's Intel based, and we equipped it with 0.5 gigabyte of RAM and an 80 gig hard drive to be able to have more than enough storage for all measurements you can imagine. It's multi-radio capable, and as you can see, there are 2 onboard mini PCI slots. You have one PCI slot where you put the riser card, so you can have 2 PCI cards in that. The hardware we're using, I think, is also the same. It's the AR5212 Atheros cards, and we use both mini PCI and PCMCI cards of that. We have the antenna, which you can see on the top as well, which is a 5 dBi Omni antenna at the moment. And for software, we're running Linux. We're using the Mad Wi-Fi driver for the Atheros cards, and we're using Click to do some things I will talk about later. And for routing protocol, we're using different ones for different purposes. So I didn't mention it specifically which ones.
Just curiosity question. So the mini PCI cards, are they on top of each other?
No. So it doesn't show here, but it's actually located here. So right under here, you would have the similar interface there. So there is so side by side. So one interesting thing that we found out, I think they are mini PCI. I don't know if they're called 3A or 3B. So this slot is for the smaller form factor, which is like 2 millimeter smaller than the other one, but the cards are the bigger ones. So we actually need to bend some of the small things here just to fit it in, but it just fits in, but it's very, very tight. Something that before I bought this node, I didn't know that there were 2 different sizes that has a 2 millimeter change in size. So we also have some other things in the testbed. The Thomson wireless card, a multi-sector antenna, and we have a software framework for cross-layer information. And these are the things that I will talk about as well in the testbed part of this talk. So starting with the Thomson wireless card, it's an ABG card, but it's actually not a PCMCI card or a mini PCI card. It's actually a full-fledged access point. So what you see down here is the access point board and the radio board. That picture is a prototype. So the final product will be slightly smaller. I think it's supposed to be 14 centimeters by 5 centimeters approximately. So this can work then either in AP mode as a standalone AP, or you can put it in station mode and you can use this at the client, or of course we want to use this in ad hoc mode. So since it's not have these regular interfaces, you need to communicate in a different way with it, and you communicate over an Ethernet interface. And that has some advantages, is that it's very easy to physically separate a lot of radios that you have at the same node without having the loss of long antenna cables, for example. So one other specific thing is that, so given this, there will be no driver running on the host. So all the MAC layer happening on the card itself. So it's a driver and the firmware and the microcode. So one good thing for us is that we plan to do changes to this, right? So there's no assembly code, but everything is in C++, which makes life a lot easier. So I'm just going to flash some features of this. So there's a reference implementation currently, which is under Windows, where you have some tools where you can get statistics for the MIB, etc. And these are planned to be ported to embedded Linux in the future. The board supports band switching, so you can run the A band and the BG band at the same time. You can do per frame power control. And what we are more interested in is, of course, the API. What kind of programming facilities exist? So one thing is that you download your code when you run. You either do it over the MII is the Ethernet, or and SPI is the serial port interface. And one interesting part is the trace and debug that is coming with this card. So I show you a slide here where you see that it is a debugging feature at the end, which reaches all the way to the lower MAC. You had a question?
So you're saying you have full software control on the Mac?
Yeah.
How does it really work? So can you set the AIFS duration? Can you set all those parameters?
So I should be very honest with you. We received the source code a couple of weeks ago, and we just haven't started doing modifications ourselves. So I'm penetrating the code to understand everything you can actually do. But since you have the full source code, which means that you can do virtually anything you want. You can throw it all out and write your own code, or So it is all the way down to the microcode.
So no part of it requires for you to write microcode or assembly. So that's something that was clarified to us.
Can you comment on the efficiency of this, in the sense that it's going to when you compile it and run it, it's going to be through an object code rather than previously like a firmware concept, right? Like the existing start.
So that we have not investigated yet. So this board is developed by a separate lab at Thomson, and we have not yet been doing performance tests with the current source code. So I would say this is very much ongoing work that we are doing right now. So for the questions about that, I do not dare to give you an answer because I don't really know. So any indication wouldn't mean anything.
Do you even know what is in the hardware which you cannot change versus what is in the software?
That is a good question as well. That I would not know exactly which is the lowest part that you would not be able to modify.
And you say you can change the power for every packet.
Yes. Yeah.
Chances are it's timing.
What?
Timing stuff. Chances are that you cannot change.
Yeah.
In our cards, like
It's the same thing in hardware.
how about ACT?
That's everything is timing related. So you have to respond within certain time. Usually there is either a microcode or something that.
So you can't have non-standard IFS, but I don't think
That's what.
They might have ability to change, but
it will be overruled by
no. You
have
can
to
probably
study.
set it.
You have to study very carefully the state because you don't want to mess up with the state machine. Right?
Exactly.
Of course,
So
it's
that's-
C code, but
Exactly.
you have to be very careful on. But you have the ability to do it. So
I would suspect you probably can control the CW min and those things, but you probably cannot control.
No, I'm sure you can do more.
you can do.
You can do a lot more. The problem is that anything that's timing related is probably. You can do it, but you screw up the stuff.
So you could basically do everything that is not realized in the hardware. That's what you can control. But then if you will be able to do that in a good way yourself, I don't know. might take sufficient, it might take extensive time to do sophisticated changes, because this is not, it's not very easy.
You have TCP IP in your Mac API?
No, that is transmit power connection.
Oh, that's
TPC. That's transmit power connection.
Oh, yeah.
And IPS?
That's who it's upper side.
And will this be available to play with? Because this is pretty cool.
Yeah. So the way that it works is that students coming for interns sign an NDA, and they should be able to play with these tools. For companies, we have a big problem, of course, but it should be able to arrange. But I cannot, promise something, right now. But we will have interns this summer who is actually going to reprogram this access point for us.
No, but
We
but
have the
not
same
also
problem.
Thomson related employees. So now we are also talking with having partners signing these NDA agreements and having access.
Well, we have the same problem with Intel. A couple of people here play with Lexical, right?
Yeah.
And everybody had to sign the NDA, which means it's pretty much unusable anymore.
Mm-hmm. Mm-hmm. Okay, I go on, and I'm moving to the next hardware of Thomson, which is something which is also ongoing. It's a multi-sector antenna that we are currently trying to design to use for our mesh networks. There are some obvious benefits, of course. So the classic one, when you talk to antenna people, think about sectorized antennas. They say you improve the link budget, so which means that you have a higher battery. A higher bit rate, and you have lower packet loss, which means you gain and you can get higher throughput. Something that we would be more interested in is to get the higher throughput by decreasing the interference, to have the spatial reuse. So one other thing that is very convenient for us is, compared to MIMO, where you need to change your RF part, you just plug this to a regular wireless card and it works. So the objectives that we have on a higher level is to do topology formation on a larger time scale, to try to understand how you choose the different selectors to form certain topology to optimize your performance. And also, if you want to do sector switching at a smaller time scale, so you can do some certain kind of scheduling using that, or if you have a fast sector switcher, you can even imagine that you don't need multiple sectors activated at the same time, but you can just scan them around very quickly. So we have an antenna which is called the Vivaldi antenna. So it's a prototype that we currently have. It runs on 11A. It's about 14 by 14 centimeters big. It's a flat antenna in that size. So basically, if you see, let's see if this one works. So these parts are the different sectors, and this is the feed to the antenna. And here is the feeding network on the backside, where you feed in the transmission signal. So currently it supports a 120 megahertz band, which is about 6 channels in 11A, and you have a 23 dB isolation between the antennas. So of course there are some challenges with this. So one specific challenge is, what happens when you activate several sectors at the same time? How do they interact? You also have, you need some control over the switch. So you need a software control of your switch. So from the higher layers that you can control this switch on a small time scale to be able to do the appropriate switching. And with the switching also comes an isolation issue, because if you have a switch, you need to make sure that nothing leaks back and goes out on the sectors that you did not have activated. So of course you need some kind of also some cross-layer integration with your with your Mac protocol to be able to efficiently do this. So I will show you now some slides about the radiator pattern, so the challenges. So now we have one antenna activated down here, and you have the radiation pattern here. So this is simulations. This is approximate how it looks. So now if you activate 2 sectors, it looks like this. It's not like a perfect, one sector plus the other ones, but it looks a little bit different, and you have some points where it's a little bit lower. You activate 3, and it starts to look even more funny. Now you can hardly say that this is the backlobes anymore. It's not so obvious. And you activate 4, and you have what you wanted to be the omni antenna, right? And you can see there's a lot of null points here. In practice, these null points might not be this bad, but due to multipath and similar effects, these will average out a little bit. The beams will not be this high, but they might be here. And the null points will not be null, but they will be a little bit better. But still, it's a challenge how you physically design your antenna and with your sectors to not end up in reality with something like this, because this is obviously not what you want.
So this is a simulation result?
Yes, this is simulation result.
What is the red one?
This one is supposed to be the picture of the antenna, which is this antenna. So with the sectors. So this is just here to say which of the sectors that were activated.
How do you select multiple sectors simultaneously? How do you activate?
So you have a switch on the backside that says, okay, now I want to feed these 2 sectors at the same time, or these 3 sectors, or all the sectors. So that is currently an ongoing design, how to design this switch so this does not leak signals back out, but it gives you still a fast switching and full control. So you want ideally, in the case of this, you want to have all the different states, 15 states that you can select.
And it's 2 dB insertion loss, right?
Yes, that's what it says. 2.3 or something, I think. No, 2 dB insertion loss. Yes.
So you need 8 dB of gain back if you turn, variable gain 2 to 8 dB.
Uh huh. So let's see. Okay, so that's is the part with the antenna, and hopefully we will have some prototypes available during the fall. So that's ongoing work. Now I'm moving to the software part of it. So this is probably a little bit similar to what you have in Orbit. So we have this cross-layer framework where we modify the Atheros driver to support the collection and the transfer of the measurements on the lower layer. So you have the RSSI, you have the raw MAC packet loss, and the transmit rate. So what we do here is that we collect all this, and those who know the Mac driver knows there is a buffer that collects some statistics. So we do this here, and we are creating our own buffer here, which is then acquired by click, so reading this buffer, or actually reading it through the proc file system. So you get periodic results from this, and then you feed this up to your routing protocols. So you use then all these metrics that you can require down here. You can use it for your routing protocol up here. So this pretty much concludes the part of the testbed overview. I will give you some example here of a routing metric which is utilizing these kind of metrics. So it's what we call the expected throughput, which is at this stage is a model which extends the current ETX and ETT. So ETX, ETT, they're looking at the physical layer at specific thing. So we want to do a little bit better because we want to take the MAC into account, because there is a clear coupling between the capacity of your links, depending on how your neighbors have selected channels and who is active. So of course then in the wireless world we all share the same channel, and here we are thinking that the link quality is not the bit rate, it's not the success probability, and it's not the RSSI, but we think, okay, it's a throughput. How do we then optimize the throughput? So there is a paper from Hoyes et al. Which says there's a MAC time sharing effect, which they call the anomaly of 802.11. Basically, it says when you have 2 links in the neighborhood, you have a slow link and a fast link, they will have the fair bandwidth sharing, but it's not in terms of time, it's in terms of the opportunities to transmit. So when you send with a low bit rate, it's going to take a very long time. And then it's the fast guy's turn to send, but he will then effectively be affected and not be able to transmit faster than the slow guys. So you will end up with a harmonic mean here and see that both of them reach just below 1 megabits per second. So what we then do is that we formulate a model which says we take the harmonic mean of all the links on the path that is interfering with the sender, and we also throw in the packet success probability similar to ETX, and then we say on this link the expected throughput is your bottleneck link. So these things in the same spirit as ETX and ETT. So the novelty is that we are capturing then this anomaly to be able to do a better prediction of what will really happen. So this is ongoing work. So we have an implementation, and we are in the phase of validating and comparing the results compared to ETT and ETX.
So this is downlink or kind of where there's an access point and there are many stations are talking to access point. Is that how?
Now I didn't follow.
No, what the model? What is the model of this?
Pairwise, doesn't matter.
What is the network topology?
Basically, this will be in the backhaul, in the mesh. So
Yeah,
your
yeah,
laptop
yeah.
won't see any of this. It's in the
Yeah.
interconnected mesh.
No, you're talking about some harmonic mean of what links are you talking
All the links on your path, on your backbone, that will interfere with your transmission.
This is mainly the simplest example. You have one access point and two users trying to access it, and they have different data rates. So that's mainly the single fault kind of example.
But you look at them as pairwise, no? They share the channel, but you don't necessarily model them as an access point, as a shared resource. They can be independent communication.
Yeah. Here it's over the full path from your source to your gateway where you look at. So you look at all the ones on that path that will interfere.
No, the fairness is flow fairness or link fairness.
So what do you mean by?
In the previous slide, you have some fairness notion. Is that
So it's the bandwidth sharing mechanism.
Yeah, I think his confusion is whether it's in a multi-hop setting or is it one hop. So it's one hop and multiple sources.
So he's just considering two links. They can be either an access point and two clients, or they can be two ad hoc links on the same channel.
To a number of within a contention region.
Right.
Yeah, this will be the same.
They're competing with each other. One
They're
link
sharing
is
channel.
1 Mbps, the other link is 11 Mbps. What is the cumulative throughput?
if you're doing time sharing?
If you're using 8 to 11 sharing.
So one assumption that I did not mention here is also that all the links are saturated at this point to have the model to be accurate. So of course you want to extend this also to not be just the links on your path, but you want to have all the links in the network, but that becomes a much harder problem because then you have the interdependence on how you select your route will affect your routing metric, and your routing metric depends on which links are active. So by this slide, I'm going to hand over to Theodoros, who's going to talk about his, he's going to tell himself, and you're going to wear this, by the way.
So during the changeover, I have a question regarding decisions you took at a higher level, where you decided to design a new antenna, and you decided to use your own hardware. So you had the option as a designer to use existing hardware and say rewrite the driver or get an NDA from say an existing manufacturer like Theodoros, or you had the option where Thomson gives you everything that they build. That was one option you had, and the other option you had was to use the existing antenna. Why did you make the decisions to go with your own hardware, to go with your own this thing, and why did you choose to design a new antenna?
So the reason is that there is a Thomson lab who is doing antennas, who are doing directional antennas. So we want to see what is the step to do a multi-sector antenna and also be able to control it through a switch, which is something that I'm not sure exists on the market that you can do it. And also trying to understand, so how does these patterns look when you activate several of them? Because typically you would just want to have one sector at a time. That's what is the typical usage. So you improve your link values for that, but we want to be able to play around with the topology and have any combinations of the sector activated at the same time.
And the most important thing is that, first of all, the geographical proximity, they are there. They are willing to work with us and say, hey guys, we're going to build a mesh network, tell us, the network layer or the higher layer requirements, and we build it.
Okay.
And of course, then we see what are the challenges there, and so of course there's a much more direct interaction than just saying here is a specification, build it, and so that's something that makes it more attractive.
So your antenna guys believe that you can improve the mesh network by using multi-sector antennas?
Well, that's something that we believe.
Okay.
We all believe.
So when you design the routing protocols, you will also take into account the directionality of antennas?
Not at this point. I mean, in terms of, I will do the presentation, and then if we can discuss about this question. Okay. So my talk essentially starts by, in a way that the original, the beginning of this talk started, is that .11 essentially based mesh networks are extremely popular these days. And the reason is that as a standard it's fairly mature, they are very low cost, and they can support high data rates to users in comparison, for example, with other technologies like 3G. Now, all those mesh networks essentially use, and my talk will focus on the MAC protocol here, they use a decentralized carrier sense based MAC protocol. And essentially those protocols in general, they work by nodes contending using carrier sense to listen to what their neighbors are doing, and if once they listen to idle channel, essentially they take a random backoff and they try to contend in this way. So there are several problems that appear at higher layers that have to do with severe throughput imbalances that the links get in a mesh network, and several times having complete starvation. And this has to do with the fact that this MAC protocol works pretty well better on single hop topologies, but in multi-hop topologies things become weird because some nodes have a different view of the state, other nodes have another view of the state, and these create all those bad effects. So essentially it is very important to somehow try to understand the operation of the protocols themselves, try to model them, and then try to invent solutions for those problems that we see here. So in general, the contribution here is that first of all, the first challenge is modeling this network. So suppose you have a set of .11 flows contending in a multi-hop network. Everybody is doing it using a different sense of the channel state. And therefore the question is, can you predict which flows are going to die and which flows are going to be dominating in the long run, as if you were afterwards running the experiment. So it's let's say a modeling problem in this sense. And previous models, for example, they were doing some assumptions in the sense of my link, for example, will get lower throughput if it will contend, for example, with more neighbors, right? So this was an assumption. But however, we began with the observation that this does not actually happen even when you run NS simulations on this. Okay, and the reason is that there are several effects by the MAC protocol itself that shift your entire distribution and do not give you this performance. So essentially, we have a model that can essentially predict the per flow throughput for such multi-hop topologies that employ .11 MAC. And more importantly, give, let's say, a more formal look onto why some flows will receive zero throughput in those networks. These enabled solutions have to do with decentralized MAC protocols that essentially are targeting for preventing starvation. And what they is how we can use such models to be able to find very high throughput paths or high throughput paths in a mesh network. And this question also links back to the fact, to the other question that says there are some existing routing protocols that also somehow try to capture what is going on in the lower layers. So the question is, do these protocols suffice, or I need something more sophisticated or some additional information, and what this information is. So this is the general problem that I am going to talk about today briefly. So first of all, I will give an overview of the .11 analytical model of our approach. Then I will move to the technique to compute available bandwidth over paths, and then extend to finding maximum throughput paths according to a metric and compare with the existing routing metrics that exist in the literature. So the model is as follows. We start from the premise that every node in the network will not see the same thing. So if you imagine that this is the timeline of what the node experiences during its operation, it has some transmissions that, and suppose that it transmits over one link, there are some transmissions that are successful, some time spent during doing back-off, random back-off, which are idle, some time lost for you to detect that a packet has been collided, and this is some time lost while you are listening the medium busy by other nodes in your neighborhood. And essentially this timeline is different for each node in the network. So if we view it as a Markovian model, then the throughput that, the useful throughput that the link would get is the probability that this event will occur divided by the average duration of any of these distinct events that are here. So to derive this, let's say, throughput formula for a node, we have the following quantities. So one quantity is that the probability that the node will actually try to send a packet. The other is the probability that given that it tries to send a packet, that's why it's conditional, it will experience a collision. And then this quantity B is the probability that when a node starts to try to sense the medium, essentially it will sense a medium busy by the other nodes in the network. So essentially, those three variables can be used to express the steady-state probabilities of each one of those events. So the success is the probability that the node will send a packet multiplied by the probability of success, and so on for each one of those events. Now, if we take a weighted average of those events and the times, then we get the average duration of the event, which is essentially the denominator of our throughput formula. And this quantity here is the denominator of our throughput formula. So this is the throughput formula. So this throughput formula gives you the throughput of a link as a function of a connection, as a function of its packet loss probability, and as a function of this probability and the average duration where it adheres the busy time interval.
Where does it factor the random back-off time?
So it's an equation that I write here. There is an equation, a nonlinear equation that connects the probability that I will transmit with the packet loss probability. If you are familiar with Bianchi's model, there is a function. So essentially, this is a linear system of those unknowns. Now, of course, yes.
Question about the system. It's probably 3 by 3 because his system is 2 by 2 and relates tau and p. So yours is probably like, since b also plays.
So the thing is that there is a separate throughput formula for every link in the network. So you have 50 of those variables if you have single links in your network, right? And of course, there is a corresponding number of other formulas. So it's like it's a much more complicated nonlinear system of equations.
So does B here capture the number of nodes contained in the channel?
It's not the number of nodes, but essentially it captures the fact that I'm going to listen to a busy medium if I'm trying to contend. But it doesn't tell you this is going to be B if the number of nodes is 5 or if it's 6. Okay. Now, essentially, the modeling problem that we started with, and essentially to try to compute the throughput and predict the throughput, essentially boiled down to accurately computing those quantities for each connection in the network. And if we could do this accurately, then we would be able to predict the throughput and answer the problem which people dominate and which people get very, very low throughput. Okay, so the thing is that there exist scenarios, even for example with two flows that are contending with each other, that one flow will experience, for example, a very large P, packet loss, for example, and the other will not experience anything, right? So you see a very high imbalance, even if they are within a region and a simple model will tell you they will get equal transmission opportunities. This doesn't happen. Okay, or there are three flow scenarios where you can simple scenarios where each flow experiences very high busy time because two other flows are transmitting and are not aligned with respect to each other because there is no such mechanism in CSMA. So that was essentially the prediction problem and gave some insights on what the MAC is actually doing. Now, this equation is for a link that is saturated, meaning that it always has a packet to transmit. So once it succeeds or it fails, a new packet is there, right? So essentially, we can actually express the throughput of a link in a more general formula where an input is, let's say, the input rate of a link, how much input the link had, so it may be at some point idle the buffer or not, the packet loss probability again, and this fraction of busy time, which is the fraction of time that the node, the transmitter node of that link, was sensing the medium busy. So essentially the throughput is given by these three variables. Now, so the modeling problem was to accurately compute these quantities analytically, but then we were trying to do other more cool stuff. Like, for example, I can, of course, as a node, I can measure these quantities and also measure my throughput, right? So the throughput that I get by measuring those quantities is not so useful for me if I want to do some predictions, right? But how about being able to measure some quantities and then compute some predictions of the throughput based on some other quantities? So this gives us the motivation to think about available bandwidth estimation, routing metrics that are based on these quantities, and so forth. So that's the continuation of my talk. So first of all, let's take this problem that we have a flow coming in the network, and we want to compute the available bandwidth on the path. So what happens? Every node measures locally the packet loss probability on its adjacent links using one of the techniques that have been developed here, for example, or some higher layer techniques where you send broadcast packets. So this is typically easy to do in a single hop. And this quantity, the fraction of busy time, which is a passive measurement. You just measure over an interval what fraction of time you were sensing the medium busy. Okay. Now here comes the second part. So now for each link, a node computes a quantity that is based on this equation. So essentially the hypothesis here is that these quantities are measured in the current interval. So I'm trying to ask now, what is the maximum possible input rate I can push on this link, hypothetically, right? So that I cannot saturate my network, so my queue does not blow to infinity. So this is a hypothetical computation locally done at each node for each one of its adjacent links.
I'm a bit confused. What's the difference between P and PL?
So here I dropped the notation.
Again, okay.
So that's per link again, but it was a single transmitter receiver. Okay. So essentially, so the idea is you use this equation, you measure those quantities, you don't try to compute them and solve the modeling problem. You measure those quantities, and then you hypothetically try to increase this rate and get a feeling of what would be the throughput that you could get based on the environment around you that is summarized by those variables. So these are some numbers. So these are some, let's say, capacity of a link, or you can view it as is if it was operating individually over the path. So, but of course the thing is that if you try to push traffic according to the minimum of those capacities, you would not probably get this, because the throughput is also limited by what the intermediate links do in the path. They interfere with respect to each other, as Henrik mentioned previously. So let's take an example. And what do we do by that is that, let's say, suppose we have 4 links here on a path, and one connection that we want to compute the bandwidth, right? So let's say that the nodes use the model to compute those individual link capacities. So what we do here is that we take groups of links on the path that will interfere with respect to each other. Okay? And then we say that in order to be able to push the maximum possible amount of throughput on this path, essentially each one of those links should get equal bitrate, equal throughput on it to maintain the flow balance equation. So this means that this should be shared equally